Good morning. Hello, welcome everyone. Today we have a new seminar, in this case given by Isabel Rodríguez. So thank you, Isabel, for coming here. Isabel is working in the nanoscience, and today is going to speak about bioinspired nanotechnology. But first, let me say a few words about her. She graduated in pharmacy from the University of Alcalá and received a science PhD from the National University of Singapore in 1998. She was a visiting postdoctoral scientist at the Sensors, Actuators and Microsystems Laboratory in the École Polytechnique Fédérale de Lausanne in Neuchâtel in 2000. And after that, she worked at the Institute of Materials Research and Engineering, A*STAR in Singapore, where she became head of the patterning and fabrication group. Then in 2013, joined in the nanoscience as a senior research professor, and her research work is focused in areas related to the application of polymer nanofabrication technologies to develop functional and biomimetic surfaces for the control of interfacial interactions, wettability, cell adhesion, and optical phenomena in applications such as nanostructured anti-reflective surfaces, super hydrophobic surfaces, or self-cleaning surfaces with antibacterial properties. So again, Isabel, thank you, and please.
Thank you, Esther. I think now you can hear me. Thank you, Esther, for the introduction and inviting me here to give a seminar. Thank you all for coming or for listening. I hope you. I'm going to give a wide talk about the work that we do over the last years, focused on mimicking nature, and that's why the title of the presentation is called Bioinspired Nanotechnology. Okay. So to start with, I wanted to highlight to you the fact that nature is structured at all levels, from the molecular level all the way to organism. Nature is highly structured and organized, and the properties that nature has depend to large extent on this organization. So this and the functions that these materials can perform as well depends on this organization. But if we focus particularly on surfaces, then we also see that many of the properties that we see in nature, in animals and plants, depend on the structures they have on the surfaces. For example, the morpho butterfly, the color that we see is a structural photonic color and depends on the these photonic structures on the surface. As well, the anti-reflective properties the moth and other insects have on the eyes depend on the structures they have on the eyes, which are here. The super hydrophobicity in lotus leaf. Lotus lives in water and doesn't want to get wet. So what it does is to become hydrophobic, and the water just rolls over it. So it's also due to those structures. The anisotropic wetting for rice, the gecko adhesion is due to the structures on the pads, as well as the hydrodynamic and non-adhesive properties and shacks, and so on. There are many other examples in nature. But most of the, in general, we could say that these skin textures are complex structures, hierarchically arranged, and at least one of the levels involves a nanometer size range. Okay. So yeah, this is some structures found in nature. We can see they are very complex, and there are combinations of size and shapes, different designs. But in contrast, we find the man-made products they have a function that depends on the micro size scale, and the surface hardly is not we don't give it a design. So we are missing to provide some properties to industrial products if we could provide them with some structures. So how we do that? So one approach is to look at nature to find the design rules. And then we can use nanofabrication tools to achieve that. So in our lab, what we do is, as a nanofabrication tool, we mostly focus on Imprint lithography. This is a replication process, as it says there, and what it does is a mechanical displacement of a flowing resist material due to pressure. So these are the schematics of a process. It's very simple. As always say, it's like making cookies. So you have actually a mold where it has the design of the structures that you want to make. Later I'll tell you how we make this. And then you can press it on a thermoplastic after you heat it up. And then because of pressure, the thermoplastic will flow into the cavities of the mold, and after cooling down, you take off the mold and then you get the structures, just like making cookies. You can also use other materials, like UV resin monomers, polymers that be cross-linked with UV light. In this case, you spin coat the material, you press it with a transparent mold, you apply UV light, the polymer cross-links and fix the structure, and then you can take off the mold. So we can use these structures, so you can post-process these substrates. That's why it's called lithography with other processes. But we typically will stop here. We will make use of these structures, as you will see along the talk. So the tools that we need to do this are then the mold. As I mentioned, the mold, it can be different materials, typically silicon, quartz, but also silica, nickel. We can also use polymers. We can apply this to substrates, but they can be any substrates actually. And the materials that we imprint usually are materials that they can flow. In general, we use thermoplastics, any of them, but it can be liquid monomers if we can cross-link them with UV light, nanocomposites, solid materials, a wide variety of any of materials. It's actually one of the most versatile fabrication technologies. And then, of course, we need equipment. Typically, it's a hot press with a UV system incorporated. And then I put here, if this mold is made out of polymer, we call it soft nano-imprint lithography. And that's something that we have developed over the years because it's very practical and it gives you a lot of freedom and improves actually the quality of the imprint after reducing defects. So the mold, how we make the mold has to be made with direct writing techniques. This obviously is the most critical part of the process. So depends on if we are working, we're trying to make structures on the micrometer scale or nanometer scale. We use different technologies. For micrometer range, we can use photolithography, to create structures that you pattern in a photoresist material. And if we want to create structures on the nanometer range, then we have to go through other technologies like e-beam writing or focus ion beam or some technology that allows to have a high resolution. So this always needs some post-processing. So then you have other technologies for post-processing that could be plasma etching if we want to etch into silicon, or we can do electroplating, or we could actually replicate those structures with another polymer. That always is with okay. These are images of molds, so it depends on the structures that we want to produce with the functionality that we want to achieve. We design the structures and then we make them. So these are some examples. So as I mentioned, we mostly do soft nil in the lab, and all it means is we have the master mold that we have made typically in silicon through E-beam or photolithography, and then we replicate it to an intermediate polymer stamp, a material that is very easy to imprint and is not adhesive. And then we replicate that into silicon, PDMS, and then this is our mold. This is cured by thermally cured, so it's an elastomer and is heat resistant. So that's what we use that as a mold. And because it's elastomer, it can adapt well to surfaces and can be demolded easily, so it has a number of advantages. So yeah, that's how we replicate. So sometimes if we want to imprint or produce structures which has very high aspect ratio, let's say in the nanometer scale, 200 nanometers pores of 200 nanometers and 1 micron height, that's called a high aspect ratio, something like this image here. Typically, in this case, we need to make use of capillary pressure. So in this case, that is achieved by having a material and a mold that are compatible such a way that the material wets the surface of this mold. So then by capillary action, we have here a force that fills the cavities. Yeah. So this is very, it's normal the case because most polymers, when they are fused or they are homonomers, they wet most materials. So this is the typical case. So by capillary action, more than the pressure that we apply, the mold can be filled up, and then we can get very, very high aspect ratio structures. Just to highlight what is nano-imprint lithography in the map of fabrication technologies. Actually, I have mentioned it a little bit with you. We have direct writing techniques, so I think those are nanofabrication techniques and include E-beam, direct laser lighting, two-photon lithography, scanning probe lithography, techniques that you directly write. And then we have techniques that provides replication. And these are mostly optical lithography, X-ray lithography, and an imprint lithography. So those are the suitable techniques for manufacturing. That means for replicating and creating materials with nanostructures at acceptable cost, let's say. Otherwise, it will be prohibited. So this is a graph where for high resolution techniques, if you want to have very high throughput and low cost, then nano-imprint lithography is in the format of roll-to-roll is one suitable technology. So that's one of our drives to do nano-imprint lithography because we hope that it can be actually applied to real products. Okay, so I will give you some examples of biomimetic materials that we have made in the past using nano-imprint lithography, and these are listed here. So I will start talking about Gecko, then super hydrophobic lotus, and anti-reflective moth structures. And then if I have time, I will move to some application into biological materials, materials for biology applications. So I'll start with the Gecko. Gecko-like, these are called dry adhesives because they don't leave mark. It's just like gecko. It's an adhesion that is mediated by van der Waals forces, so it's not a sticky adhesion. So inspired by the gecko pad. So this is an image of what is on the gecko. It's a very hierarchical structure of many levels. They have 4 levels on those branched fibril structures. So includes a set of 4 microns that divides into branches of 1 micron and finally divides into branches of 100 nanometers. The interesting part of this is the aspect ratio of every level is very similar. So what it does, all this hierarchical structure, is to provide a very conformal surface to reach contact with other surface, and that is what allows to van der Waals to be developed, and that's what creates adhesion. So it's just because allows the contact, this compliant structure. I put this, I think it's quite interesting, like comparison of the adhesive attachment pads of different animals, and it turns that the smaller the animal, the bigger the attachment pad. From this ladybird or lady, yeah, ladybug, to the gecko. Yeah, you can see the it goes from 2 micron to 100 nanometers. So it's quite interesting. So as the attachment pad becomes smaller, becomes also branched and more compliant. That's what happens. So then it comes the engineering, how we make such fibrillar branched structures. So what we developed at the time is we developed this small base on porous alumina. That is aluminium. When it's anodized, it creates pores of aluminium oxide with nanometer range, and it can be is organized like is shown in here. This is the process. It's a reaction, and we develop the process stepping down the voltage so we can create these branches on the mold. I don't go into details. So we have all these branches, and this is the real mold, the real template, and you can see the branches going through the mold. So this is the mold that we use to imprint in polymer materials. So these are results. This is polycarbonate, yeah, a normal thermoplastic polymer, and you see the structures. These are like 500 nanometers branched in 100 or 200 nanometers. Different designs depends on the process, the anodization process. Yeah, these structures are also hydrophobic. It's just like gecko because of this hydrophobicity, and small structures are actually self-cleaning. The gecko doesn't has the parts very clean. Otherwise, it will stop walking. Yeah. So this is this is stuck in a coin. Is one of those tapes that we make, and you see that the adhesion. The gecko adhesion is actually a frictional adhesion. That means it only sticks when there is a shear force. That's why the gecko, when it walks, it applies a force, that is the shear force that engages the branches, and when it releases the force, it can move. The adhesion stops, so that's why the gecko can move fast. It's adhesive, but as the force is released, so in this case, the force is done by the weight of the coin. So when become more than horizontal, we don't have a shear force anymore, so the coin drops. So that's what it is. So yeah, when we measure actually in the lab the adhesion, the frictional adhesion of these tapes, we see that is similar and comparable to that determined on the gecko. So that's the graph. These adhesive tapes now have been commercialized. For example, they have wide interest in robots. You can go to the MIT biomimetics robotics lab, so they have these gecko tapes, the same principle but different designs. They put it on the parts of robots so they can climb the walls. There are also some applications in medicine because there are clean dry adhesives. They don't leave residues and so on. So they made it to the market. And I want to talk a little bit also on super hydrophobic lotus leaf, how we replicated this, just to highlight a little bit on what is super hydrophobicity and what is wetting. So how it's defined is by a drop of water on a surface, and that's given by the Young equation, give us this contact angle. A drop of water mixed with a solid surface, and that depends on the surface tension of the interfaces. So that's a flat surface, and when we have a surface with the structures, then the water may wet all the roughness. That is called a Wenzel state. So in this case, we call this apparent contact angle, and is modified by the roughness parameter. But to have a hydrophobic surface, we actually need to have the water sitting on a surface that it doesn't wet. So it creates some air pockets below the water. In this case, the apparent contact angle is modified by this fraction of surface that is in contact with the water. So to say that surface is hydrophobic, this contact angle, this apparent contact angle, has to be above 150. So that's considered as super hydrophobic. And it only happens if we have topography. Otherwise, it can only be hydrophobic. So that's what it means, super hydrophobic, water that hardly touches the surface. Another property is self-cleaning. That means the water rolls on the surface. It doesn't stay. So that's called self-cleaning because when those drop of water roll on the surface, they trap particles and they clean the surface. So that's what it comes. So in this case, that's another parameter. Depends on the contact angle of advancing and receding. The difference on these angles have to be below 10, and then you have a water that rolls on the surface. So this we can have a super hydrophobic surface, for example, as I mentioned in the lotus leaf, but rose has also a super hydrophobic surface, but the water doesn't roll. As you probably have seen in the roses, they have the water droplets on the leaves because the rose wants to have the water to be fresh, but the lotus leaf wants to roll the water. Not to get wet because it's on water already. Okay, so how we copy this artificially? So this we always have to make them all. So how we make them all? The process is there. We have to make a hierarchical surface. So in this case, we started with some domes. To make the microstructure, and then on them we produce this anodic alumina, which is the nanostructure. So we have the hierarchical micro nanostructure imitating the lotus, and then that you see here. So that's the structure, and this is the characterization data. So we see that we have a very hydrophobic structure. So I have a video here. So what it means is when you put when a drop of water goes on this surface, it almost rolls by itself. It doesn't really stay. Just the air in the lab, it will bring it away. So that's that surface. Yeah. Another example, biomimetic, is the anti-reflective structures of the moth eye, as I mentioned before. So this is the this is the moth. This is the eye of the moth. It has these domes, but inside these domes it has these little conical structures, very, very small, as you can see. Scale is 100 nanometers, so this is 250 nanometers at the bottom and 80 nanometers on the top, very small. And this, the moth eyes are anti-reflective because it lives at night and it wants to trap all the light, and as well it doesn't want to reflect light to be caught by the predators. So over the years has developed these eyes. So reflection, just a little bit to highlight what is reflection. Reflection happens when a light goes across an interface with has a different refractive index than air. So for glass, for example, we see here the light is transmitted 92%, but 8% of that light is reflected. So that's what we see in the mobile phone, etc. Right? This reflection, and that's yeah. No, the video is not here. So those reflections obviously are annoying, and for many applications like solar devices, it means a reduction on efficiency because you are losing light. So there are many, generally two approaches to reduce reflections. Typically, it's been by using coatings with certain refractive index to create destructive interference. Most simple case is the single layer that is designed with these parameters. Is only suitable to avoid reflections of 1 or 2 wavelengths. Typically, that's what is in our glasses. That's why we see that bluish. Or multiple layers, which are most effective, but there's expensive approaches. Yeah. And the other approach is the graded refractive index. That means create a gradual refractive index across the interface. So this is done by porosity or texture, like the moth eye. So these are actually a more effective way of reducing reflection because it's broadband. It's for all the wavelengths in the spectrum, and it's also not directional on the angle of incidence. Well, so this is the gecko, very smart nature. So that's what we try to replicate. This is a little bit different, but what we did is actually not only create the gecko, the moth eye nanocones, but we doped them with nanoparticles because we wanted to, later I explain, to make them slightly more resistant, because obviously these tiny little structures are very fragile. So we doped them with nanoparticles of titanium dioxide. So this is our nanoparticles. So these are the nanocones that we imprinted using a suitable mold with these structures. So these are replicated on PMMA with nanocomposites, because you can see here some little tiny titanium nanoparticles. So you see the dimensions here are very similar to those on the real moth eye. And these are, in this image, then that we see this plastic. Obviously, this is something that we want it to be transparent. So this is a plastic that a PET that has a hole in the middle, and here we have put a piece of this anti-reflective pattern moth eye structures. They are not visible to our eyes because they are smaller than the visible wavelength, so it looks transparent, and it has to be transparent. Then you see this is the reflection of the neon light, and as soon as we get into the anti-reflective film, the reflection is avoided. So that's what it means, anti-reflective. We can also measure it. So if we have a PMMA film, the reflection is on average 9 to 10%. If we put these nanocones structures on one side, we reduce it to 7% reflection. And if we put it on both sides, then the reflection is reduced to only from 4 to 2%. So that's the data. And sorry, and that below is the transmission, which is almost the opposite as the reflectance. But another thing that I have seen, this happens almost across all the visible light spectrum. Because we have these particles, so then we wanted to reinforce these structures so they can be slightly mechanically more stable. So we put these nanoparticles. So what you see here is some indentation test that we did, applying a normal force to the surface and see until what depth the probe goes in. So if we compare a PMMA normal nanocone structure, then you see that the depth that we can achieve for similar load or force is higher than when we put our nanoparticles. So we have reinforced the surface. So we can calculate the stiffness of these reinforced structures and similar that to a flat surface. So that's good. As well, it happens with nano scratch. I don't want to. So scratch is moving applying a force parallel to the surface. So it also, when it's reinforced, then we can see that the plastic deformation of those little nanocones that you see here, that they form when you apply the force, is reduced when we have titanium. But anyway, yeah, this is some details on the film. As well, it happens like most nanocomposites. The thermal stability is improved. That means the temperatures that these materials can stand when it's doped with the nanocomposite is higher, these nanocones. So you see here FM images of these nanocones after they've been heated up. So when we heated up, the material which has nanoparticles is stable at higher temperatures of 150 degrees, which is quite good. So this is the test. And I would like to move to some biological applications of these materials. That is also something that we do in the lab. And mostly we use them to be as bactericidal surfaces and also cell instructive. I will just touch these two properties. So bactericidal surfaces, we also use this Moth structure topography because obviously as well the moth doesn't want bacteria to grow on the ice. So these bacteria, these surfaces are naturally bactericidal. So as we know, most insects don't have bacteria growing on the eyes, on the skin, because of those nanometric size structures. So we replicated again these structures, and to see if they have a bactericidal property, what we do is to have these films that we have made, and then we incubate them with bacteria on them. And then we look at the bacteria that is dead and alive. We also study if they are biocompatible for normal cells. So here you see bacteria attached to the surfaces, these moth eye surfaces. So this is a flat film, flat PMMA acrylic film, and this is the film with the moth eye. So when you see the green dots are bacteria that is alive, and when they become red is bacteria that has attached to the surface and has died. So then you see that on the moth eye topography, we see many of the bacteria has died, is dead. And this is some quantification of the dead bacteria on these moth eye surfaces. So typically, almost like 50% of the population of the bacteria will be killed by the surface as they attach on the surface. And this is bacteria. On top is the flat surface, plastic, could be SPMM, but could be any other plastic. And below is the moth eye nanocones. And then you see some of the bacteria has really broken the membrane and released the content and die. So it's totally mechanical. It's doesn't use any chemical. So it's possibly good for avoiding bacteria resistance. Or at least it will be good to reduce the amount of antibiotics or biocidal materials. So as I mentioned, this is a mechanical rupture. So what happened is the bacteria, if this is a bacteria membrane, when it comes to a surface, it wants to attach because they want to create a biofilm, a colony. So for that, they want to attach to the surface. So as they attach to a surface that is smaller than they are, the membrane becomes deformed and stretched, and that causes the destabilization of the bacteria and the death. And we have managed to turn around these bacteria after they have attached to the surface, and you see here actually the indentation that is created by this surface. And we have measured using stereometry and AFM what is the depth of these indentations, and you see here. This is for E. coli and aureus. Typically, it ranges between 30 and 40 nanometers. So they have indented, and that is what has caused the death of these bacteria. But for mammal cells like keratinocytes and other even stem cells, and these topographic surfaces are much smaller, and they have not much effect on them. So the ability to live by the cells is normal. It doesn't affect them. So that's something that we wanted to. It's good, for example, for implant materials in the body because you want them to be well integrated into our tissues, but you don't want bacteria to grow on them. So that's why we also tested. I'm going to skip this. These materials to see how they behave. If we have a micron size that actually directly SAC, because the material normally is not the same. I mean, we use polymers. Nature is proteins. But what we're doing mostly is replicating the function, but following the principle. And yeah, so that's most of the time. And sometimes principles that they are not in nature, but so you end up obtaining some properties that they are not there. But yeah, okay. No, I will think no. Actually, you have seen many of the structures are disorganized. Like la de Lotus. And no, in that case, what I would say the order is not important, but is the size range and the arrangement. Uh, that is sometimes an advantage because you don't need to have such precision as when you go to making semiconductors structures. No, for many of these, I wouldn't think is necessary the order. We use the order designs because, like for the Moth eye, actually is the mold is made with interference lithography, so it's made organized. But we actually some researchers have copied the eye itself, replicating the eye, and yeah, it's not really ordered. Yeah, so it depends. Yeah.
Hello, I'm not from the field, so probably my question is very naive, but I see some of the structures can interlock, so because they have complementary shapes, no? So I wonder whether you test self-adhesion between the different surfaces. So one of your tests is just trying to see whether these surfaces stick each other or not.
No, we haven't done that. If both structure surface, they will stick to each other.
Yeah. So like a tape or something, like sticking tape or something like that.
Yeah, I mean, it could be like a Velcro, right, or something.
Something like that, yes.
No, we haven't tried that. There are some. I think some people have tried to imitate these Velcro type of structures, also like adhesive. We haven't try that. For adhesion, there are these, as far as I know, these two principles. One is to actually create a lot of surface contact, and another one is to engage, like Velcro type.
But some of these designs are very complementary, so the shapes...
I guess, yeah, if we manage to actually interlock two surfaces that actually you increase the surface area, then possibly you will increase the adhesion between these two surfaces. The case I know, for example, is two polished silicon wafers. You put them together and you cannot separate them because the adhesion is huge, because every point in the wafer is touching. So that's the one case when you have maximum area adhesion, but typically in nature surfaces are much rougher, so you never have such a long contact. So the adhesion is not there because we are not touching. Yeah.
Questions? Isabel, and what is the area that you can nanostructure with this technique? I mean, you are getting centimeters or millimeters or meters, and how fast is the process?
Okay. Typically, when we want to prove the principle of some surface or structure design, we do like 3-inch or 100 millimeter areas, or 2 times 2 centimeter areas. But we have equipment that it does roll-to-roll nano imprint, so that is continuous. Obviously, scaling up has some difficulties. I'm not saying that it can be translated rapidly, but engineering is another step forward. But so for some of the structures, the Moth eye, for example, we are able, we do it on the roll. So that is 10 centimeters continuous. Yeah.
Very good.
It can be done continuous in the good day. I mean, there is some days and then you have problems, defects, whatever. But I mean, the possibility is there. Yeah.
Okay.
Thank you, Isabel, for your talk. Very nice. I was I had a question that was related to the first one, because it's very interesting for me to see that our topological or geometric properties of the materials more than the composition of these materials that provide the some properties, some biological properties. It is very quite shocking. But in fact, if I understood correctly, you have replicated these some properties of the biological material with your synthetic materials. Is it? Do you know examples of some biological sources in which different topological or geometrical properties provide the same behavior? For example, hydrophobicity. You talk about lotus, but there are also an insect that runs on the surface of the water. I don't know the name in English. Do you know if
what a strider?
Es zapatero en español, zapatero acuático. No sé, I don't know in English. Do you know if different topological materials convert to the same behavior, macroscopical behavior?
Okay. Yeah, I would say most of these properties are actually achieved by the geometry, but obviously the material properties are implicit. But for example, if we talk about wettability or hydrophobicity, the rule is normally that when we have a material that is hydrophobic, when you make a structure, becomes super hydrophobic. But if we have a material that is hydrophilic, when you make a structure, becomes super hydrophilic. For example, cellulose, paper. Paper is hydrophilic. Cellulose is hydrophilic. When we make a structure, which is a paper, becomes super hydrophilic. You put a drop and it wicks into the paper. It is wetting totally. So that's a sample clear that the material properties are very important as well. Yeah. So it depends on what you start with. I mean, the material properties definitely determines the function and the final property. In terms of biological materials, in nature, most of the materials, I mean, for insects and so on, is proteins that they are hydrophobic, slightly hydrophobic. So that's why most of the insects are hydrophobic, cell cleaning, nothing sticks to them. Yeah, so there are keratin, alpha keratin, some kind of protein, kind of material, and chitin. They're actually more resistant materials than thermoplastic, like polypropylene, polystyrene. They are much more expensive. So that's why we don't use them all the time, but actually the properties are very good. Yeah. So yeah, depends. You can achieve, depends on the function that you are looking for. Then you have to consider actually the properties of the material that you have. Yeah.
Thank you very much.
Any other question? If there are no more questions, we will thank you again for coming, and this is a small present for you.
Thank you very much. Thank you.